Okay. Thanks very much. Thanks for the intro. Okay, so this talk was meant to be given by Tina, but unfortunately, she wasn't able to make it today, so I'll be giving it in her stead. Um, but yeah, so the title is about compiled non-local games from CHSH to BQP verification. So what is this all about? Well, let me just remind you of like a motivating question for a lot of work in quantum information, which is this: how do you test a quantum device? So I stole some of Tina's slides for this part because I like the drawings. But okay, so you have your classical computer here, and you have your quantum computer, and they all live in like refrigerators. So this is a fridge. Um, so you ask it. So what's like the gold standard, right? It's like you ask it to run Shor's algorithm. Like you give it your favorite composite number, and you ask what are the factors, and it tells you the factors, and then you're like, great, I can check that these factors multiply out, and so I'm happy. Um, so that's like good for factoring, but many of the problems we want to solve with our quantum computers do not have this structure. So for instance, like a canonical like problem that a quantum computer can solve that classical computers cannot, we think, is correlation. So like I give you two Boolean functions, and I ask, what's the correlation between the first function and the Fourier transform of the second function? So quantum computers can do this, and you'll ask the quantum computer, like, what is the correlation? It says it's greater than or equal to 3/5. And then you're like, how do I check this? So how do I know if you're lying? Well, I guess you don't, right? Like at least this is not a problem that's contained in NP, so like you can't actually like there's no like certificate here that proves to you that the answer is correct. Um, so yeah, we would like to have some way of knowing that the quantum computer is actually telling the truth here. So oh, I guess the animations did not make it to the PDF. Anyway, you can pretend that I unveiled the bullet points one at a time. So that was all in the study of one quantum computer. Now, there's been a lot of work on this question in the case of two quantum computers. This is actually, has a long history in physics, like predating quantum computing. If you have two quantum devices that are spatially separated, so they can't communicate with each other, then there's this whole like zoo of techniques based on Bell inequalities for testing how those devices are operating, like for certifying the physical behavior of those devices. So the most basic Bell test that you've probably all heard of is the CHSH game. And this has been implemented in reality. Like there's experiments where like the two parties are separated by more than a kilometer, and you ask them to perform certain quantum measurements, and you look at the correlations that they obtain, and that certifies that they have an entangled state shared between them. And moreover, this Bell test can certify very like precise statements about the kinds of operations that the devices perform. So it can certify that for CHSH in particular, like if you're close to getting the maximal winning probability in the test, then you know actually exactly what state the two devices are using and what measurements they're applying. Like they're applying measurements in the Pauli X or Z basis. So this idea, super powerful, comes from physics, and it's been extended to computation as well. So there's a sequence of works that show us how to boost this up to verifying any computation in BQP. So if you have two spatially separated quantum computers, you can actually check that they did correlation correctly. So I guess the first work that really achieved this was Reichardt, Unger, and Vazirani, and then there's a very elegant scheme due to Alex Grillo, which is what we'll be building on in this talk. So like the phrase that they sort of coined is that these are the correlations you see between two separated devices are kind of a classical leash on a quantum system. They're a way for us to control a quantum system even with only classical input and output. Now, that's all in the setting of two quantum computers. What if you just have one? So here, the answer came to us a bit later, but we also have an answer in this setting of what you can do. It involves cryptography. So it was shown by this work by Brakersky et al., and then the next work by Mahadev in 2018, it was shown that there's a way to use a particular cryptographic problem, the learning with errors problem, to come up with a different kind of classical leash for quantum devices. And this one shows that, so what Mahadev achieved in her paper is that she gave a protocol that, just like the RUV protocol or the Grillo protocol, lets you certify that an untrusted quantum device executed any BQP computation of your choice. And the only assumption you have to make is that the device cannot break the cryptographic assumption that the learning with errors problem is hard. So this is great, and it's like much more realistic than doing a 2-device protocol, because experimentally having like 2 sophisticated quantum devices that are spatially separated but also share entanglement is really difficult to achieve. Like even for the CHSH game, like that experiment I showed you in the previous slide was like a major effort that took a lot of work. So this is great. Now, 2 questions you might ask are the following. The first is, are these 2 things, these 2 different notions of a classical leash on a quantum device, are they in some sense the same? Like, is there some conceptual commonality, or are there two totally different approaches to obtaining control of a quantum device? So that's like the main question, I would say. And then a subsidiary question you might ask is like, for the second setting, like the 1-device setting, are the cryptographic requirements, the best you could hope for, or could you relax the requirements a little bit? So let me address what was known about the first question. So it's kind of a partial answer was known before our work. So if you look at both the analysis of the CHSH game and protocols built on it, and the analysis of the Mahadev scheme, they both have like this property that the key step is establishing that the untrusted quantum device, or prover we might say, has a qubit that it's operating on. And how do you do this? Well, the kind of perspective that one can take is that you can define a qubit by a pair of anti-commuting observables, anti-commuting binary observables. So this is what we call like an abstract qubit. So I think this point of view is kind of like put forward very clearly in these lecture notes by Thomas Vidic that explain the Mahadev protocol, and I think that's actually not quite how it's stated in the original paper, but this perspective is presented here. So the idea is that if you can just somehow certify that the prover applies 2 different binary observables on its space that anti-commute, then that certifies that there exists a qubit. There exists like a 2-dimensional Hilbert space that the prover is manipulating. And that can be done very explicitly in your analysis, that as soon as you have 2 anti-commuting observables, there's an actual map you can write down that extracts this 2-dimensional Hilbert space that corresponds to the qubit that they act on. So that thing even has a quantum circuit. It's called the swap isometry. So it turns out that both the Grillo protocol and things like it, and the Mahadev protocol, ultimately can be analyzed as using this swap isometry. Like they somehow prove that the untrusted quantum device has a pair of anti-commuting operators, and then they use that to get a qubit out, and then they build on that to verify all of BQP. So that part of the story is kind of the same in both settings, but it turns out that really that's not entirely satisfying, because most of the hard technical work in the analyses is just obtaining the pair of anti-commuting operators in the first place. And the way that's done in the 2-device world and the 1-device world looks very different. So that doesn't seem to be unified. Okay, so that's what I want to say about, are they the same thing conceptually? About the cryptographic assumptions, again, like there was some evidence that not all of the things, not all the bells and whistles and the object that's used in the Mahadev protocol are needed, strictly speaking. So if you look at her protocol, like the particular primitive she uses is something called a noisy trapdoor claw-free function pair, I think, with adaptive hardcore bits. So this last thing about the adaptive hardcore bit is there's evidence that this was not needed. And this is actually one thing in particular that was shown by Mahadev in an earlier work is that without this assumption, you can achieve something that's still pretty powerful, something called quantum fully homomorphic encryption. So that's the ability to have a client like manipulate encrypted quantum data. And a question she posed in her thesis actually is there a way to go from, in a black box way from quantum fully homomorphic encryption to verifying all of BQP? And it didn't seem like entirely obvious how to do this. So, but maybe there was like a suggestion that this might be possible. So, Okay, I'm really regretting the animations here, but so okay, what did we achieve in this paper? So in this work, we kind of try to give answers or progress on both questions. So on the first question of whether you can conceptually unify the 2-device and 1-device worlds, we give a new protocol in the 1-device world that's kind of built out of a 2-device protocol by taking a 2-device protocol and applying a kind of black box transformation to it. So this is, we take in particular the protocol of Grillo, and we apply a certain transformation due to Kalai, Lombardi, Vaikuntanathan, and Yang from 2022, something that they call a compiler, which takes any 2-device protocol of a certain form and maps it to a 1-device protocol. And we show that this compilation procedure applied to Grillo's protocol for BQP gives you a 1-device protocol for all of BQP. And the analysis for this thing involves taking the 2-device analysis and kind of manipulating it how do I say this? It sort of follows along the same lines as a 2-device analysis. Like every step in the 2-device analysis has a corresponding analog in the analysis of this 1-device protocol. So in that sense, it achieves some sort of conceptual unification of the two approaches to obtaining an abstract qubit. And then in terms of this question of like, what are the cryptographic assumptions you need, we show that the, I guess, conjecture in Mahadev's thesis is indeed true, that quantum fully homomorphic encryption as a black box is sufficient to get verification for BQP. So that's the only object we need. So ultimately, it's if you look at the concrete assumptions we need, it's not an improvement, and because both fully homomorphic encryption and the trapdoor claw-free functions that Mahadev used, like they both are built from the same assumption, which is this learning with errors assumption, but conceptually maybe it's like putting more inside the black box. So that's maybe a simplification, you could say. Okay, so that's essentially the result. So for the rest of the talk, I'll tell you about how we prove it and what some of the open questions are. Okay, so to talk about how we prove it, I'm going to really focus on kind of what I view as like the technical core of this, which is showing how to get a single abstract qubit on the untrusted device. Like how do you show in the analysis that this pair of anti-commuting operators exists? So let me review kind of what goes on in the 2-device world, and then we can see how to modify it to the 1-device world. So in the 2-device world, in general, like the type of protocol that we consider is something called a non-local game. So it's a protocol where you have 2 quantum devices, which I've called Alice and Bob. We assume they can't communicate with each other, and they do communicate with a classical party called the verifier, sometimes called the referee also. And so this classical party will like generate challenges for each of the 2 quantum parties, which are labeled by X and Y here, and they will each compute a response to the challenge by doing some quantum operation and send them back. And then the verifier will decide whether their responses are correct or incorrect for the given challenges. And we say, if their responses are correct, we say they've won the game, and if they haven't, then they've lost the game. So this is viewed as like a game played between the verifier and the 2 quantum parties. So a quantity that's super important for these protocols is what's called the game value, which is just the maximum probability they have of winning or succeeding in the protocol over all possible quantum operations they could do. So they could prepare, in particular, they could in advance prepare whatever entangled state they want. So before you start the protocol, Alice and Bob can get together and prepare any entangled state psi that they'd like, and they can decide, for any scheme they want on how, in response to a particular challenge, they obtain the measurement outcome, or they retain the response A. So maximizing over all those things, that winning probability that you can get is called omega star. So for the particular example of the CHSH game, I'll just review what it is concretely. The challenges and responses are all a single bit each. So they're all 0 or 1. And the condition the verifier evaluates to determine whether they won or not is this very simple condition that the XOR of the responses, so like the difference mod 2, should be equal to the product of the challenges. So if the challenges are, if either the challenges is a 0, then they should respond with the same bit. And if the challenges are both 1, they should respond with different bits. That's what this equation means here. And then you can describe the behavior of these two devices by they have some quantum state psi. And then you can abstract away all the operations they perform to compute their responses by just a set of 4 binary observables. So 1 binary observable for Alice for challenge 0, 1 for challenge 1, 1 for Bob for challenge 0, 1 for Bob for challenge 1. So it turns out that the maximum winning probability in this game is this magic number, cosine squared pi over 8. And you can show, essentially along the way, if you can manage to show this bound, that the maximum winning probability is cosine squared pi over 8, you get as a byproduct that for any strategy that's close to achieving this, the 2 binary observables that Bob holds, B0 and B1, are close to anti-commuting in their action on the state psi. So this equation holds where the approximation is just saying that these 2 vectors are close in the 2 norm. So this is actually the statement concretely that you need to say that there's a qubit in Bob's space. So this is what we'd like to show. We'd like to show a version of this in the one device world, that there's 2 binary observables that anti-commute on a state that's held by the device. Okay. So now let me explain what is the protocol that we're actually going to run in the one device world. This is the proposal of KLVY, the one that I mentioned. So they described a way to convert any non-local game into a one device protocol. And their proposal is this: you just take the one device, you take the non-local game and you kind of unroll it. So you ask the single device that you have to first pretend to be Alice from the non-local game, and then pretend to be Bob. So this, on its own, this idea is kind of nonsensical because the whole point of the non-local game is that Alice and Bob cannot communicate with each other. So if you ask a single device to be both Alice and Bob, then that doesn't seem to make sense because there's no separation between Alice and Bob then. All the information from Alice can leak to Bob. So they added a little twist. The twist is that you give Alice's challenge under encryption. You don't give it in the clear. So that the device doesn't actually know what the challenge is. So what is the scheme? The scheme is you have this single device, you ask it to pretend to be Alice first, but instead of giving it the challenge X, you give it an encryption of that challenge under a fully homomorphic encryption scheme, like the one from Mahadev that we saw a few slides ago. So this one is, so the point of fully homomorphic encryption is that you can execute any computation you want on X, you'll just get an encryption of the answer instead of the answer itself. So whatever Alice was supposed to do to map from X to A, this new device can now apply the encrypted version of that to map from encryption of X to encryption of A. So that's what we want it to do. Okay? So it'll do this. And then the verifier will say, okay, now pretend to be Bob. I'll give you Bob's challenge, which is Y, and I'll ask you to compute Bob's response, B. And then at the end, you decide to accept or reject in the natural way. So you decrypt the response from the first part, and then you take the 2 responses together and you do whatever you would have done in the 2-player case. So why does this work? The idea is that the encryption is like simulating the spatial separation between the 2 devices. So in the non-local case, what is true, like in the 2-device case, the state that Bob locally sees is always exactly the same, independent of what Alice does, what information Alice gets. In this compiled world, the state is not the same, because it certainly depends on X, because some operation here depends on X. But the security property of the homomorphic encryption says that the state is, the different states for different X's are computationally indistinguishable. So hopefully that's close enough to being exactly the same. That was kind of the hope, I think, behind setting up the protocol this way. So what they, what KLVY showed in their paper is that this transformation actually works if the device is classical. So if the device is classical, the maximum winning probability in this transform protocol is the same as what you'd get in the original two-device protocol. But they didn't establish this for the quantum case. Like in the quantum case, it's in fact still open whether for a general non-local game, if you apply this transformation, you still get the same game value, or whether the probability of winning can go up. So what did we show is we showed that this is not the case for the CHSH game in particular. So for the CHSH game, the winning probability in the two-player world was cosine squared pi over 8, and in the one-device world, it's still cosine squared pi over 8, plus a negligible error that comes from the cryptography. And I should mention that this is this particular part of the result is other authors achieved this independently of us. So there's this work of Brakersky et al. And also Lombardi and Ma, which I think is unpublished. This one is on arXiv. So yeah, okay, so let me, I have like 1 minute, so I'll just flash at you what we do. So really the key thing is, I said we wanted to get anti-commutation. Really, it turns out that you should think about just getting the cosine squared pi over 8. Like once you can show that, then probably you can show anti-commutation as well. So how do you get cosine squared pi over 8? How do you show this bound classically? One way of sorry, not classically, but in the two-device world. One way of doing it is through a technique from polynomial optimization called the sum of squares technique. Basically, you show that the winning probability in the game is like always upper bounded by cosine squared pi over 8 times identity. Or with this like rescaled version, it's like always upper bounded by 2 root 2 times identity. And you show that by just writing it as 2 root 2 minus some terms that are the squares of measurement operators. And so those things are just always positive because they're squares of Hermitian matrices. So what our proof was for the one-device protocol is kind of mimicking this, but under the cryptography. So what we'd like is to say that even in the one-device protocol, you can say that the winning probability is cosine squared pi over 8 minus a bunch of terms that look like squares. Unfortunately, this is not literally true, but they look like squares that are fed into some sort of map that mostly preserves positivity of squares. So the lemma we actually show is that these things that look like squares plugged into this map are still positive, assuming the security of the crypto. So if you want to see more details, I encourage you to look at the paper. So I'll just close with maybe the open questions. So what was the goal, maybe I'll say, of like KLVY when they proposed their transformation? I think that the broader picture was that a lot of work in classical cryptography sort of emanated in a sense from multi-prover interactive proofs, like the classical version of non-local games, that were then transformed in various ways into single prover or single party protocols. Like you get things like proof systems, like PCPs, argument systems. There's various like tricks to like manipulate these things. And the hope that I believe they had is that we could build up a bag of tricks that could do similar things to MIP stars, which is the quantum version of multi-prover interactive proofs. So eventually we'd have like a stable of techniques for turning these things into like single device protocols that work in based on some cryptographic assumption. So I think that's like a very promising area to work on, and hopefully this work can like lead towards that. In terms of specific questions, so one thing that's open still is like, does this transformation work for general games? We only showed it for the CHSH game and for the Grillo protocol, which is built out of the CHSH game. I should mention that like as of very recently, both like us in collaboration with Arthur Mehta and Connor Paddock and David Sway we think we have a proof of this for a class of games called XOR games. And I also heard very recently that another group has this as well. So that at least the XOR case maybe has been solved, but like for general games, we really don't know. So that's one question. And then, further, like, can we actually simplify the cryptographic assumptions in reality? Can we get better verification protocols for BQP that have less overhead than any of the known protocols that we have? Like, say, like linear time overhead would be great. So yeah, I think that concludes my talk, and thanks for listening.
short question.
Thanks for the talk. So what's the importance of having a two round protocol? Is that just for illustration purposes, or is it actually important that the questions come separately?
Oh, great. Okay, yeah. So this is a great question. It is actually important. So this does not work if you have a one-round protocol. So the question was like, why send encryption of X and get the answer and then send Y? Like, why not just send them together if the encryption is like kind of separating them from each other? And it's actually known that this does not work if you do it that way because there are kind of attacks based on non-signaling correlations. Yeah, I think there's particular instantiations of the homomorphic encryption where like you can make that version of compiled CHSH have value 1. Is my understanding. I haven't actually worked through the attacks, but yeah. So yeah, it's true, like the round structure is helping in addition to the encryption. Another question.
Hi, thanks for the great talk. You were mentioning MIP star at some point.
Yeah.
And would it be explain a bit more about what challenges in extending this to Magic Square game and combining with low degree test or all these techniques? What's
Okay.
the part of?
So okay, the Magic Square game I think actually has been achieved also independently by a bunch of people. So like I guess like Julio and co-authors have a result of this nature, and I think like Fermi and Alex, you have something, and like Tomas Vidic mentioned that he has this. So I think the Magic Square game, like it is known how to compile it. The other games we don't know, like the things like the low degree test, like the other components of like say like the MIP star, like for NX or whatever, like we don't know how to compile those yet. Yeah.
Thank you for clarification.